Hello, and welcome to our LeChateliers Principle video. And so, in a previous video, we talked about reversible reactions and equilibrium. So LeChateliers Principle deals with what's going to happen if we take a reaction at equilibrium and we somehow disturb it. So if we disturb that reaction at equilibrium, what's going to happen is it's going to shift in the direction that will reduce that stress. So in other words, what we're saying here is whatever change we make, our system or our reversible reaction is going to adjust to undo that change. So if we add more of a chemical, it's going to use up the excess chemical we added. If we remove a chemical, it's going to replace that chemical that's been removed. If we change the temperature by adding heat, it's going to absorb that heat. If we reduce the temperature, it's going to release heat to replace that heat that's been removed. And so whatever sort of change that we've made that's disturbed the balance is going to shift in such a way to try and restore that balance. And what we mean by shift is either going to shift towards the product side, in other words, make more product, or it's going to shift towards the reactant side in order to make more reactant. But our goal here is to return the system to equilibrium or to reestablish balance, to undo or minimize whatever this change was. So I had a student in the past who gave me this really cool sort of visual tool. He talked about how we could imagine the reversible reaction as being like, at equilibrium, two buckets filled with water. And there's a pipe connecting these two buckets. And so what's going to happen if we add more H2 or I2? Well, that's going to be like if we added more water to our reactants bucket. So our reactants bucket's going to be this one on the left. And so if we were to add more water to this bucket, in order to reestablish balance, the water would have to flow towards the products bucket or towards the right in order to reestablish balance. So we'd again shift towards the products or shift towards the right. Either description is clear and both are commonly used. So that's what happens if we add reactants. What happens if we add product? So if we dump water into the product bucket, the opposite occurs. Our water level here is going to be too high, and we're going to have to flow back to the left or towards the reactants. So we're going to shift to the left or towards the reactants in order to reestablish balance. So if we add product, we shift towards the reactants. If we add reactants, we shift towards the products and trying to undo this change. Now let's talk about what happens when we remove a chemical. So once again, we're going to look at our trusty buckets right here. And so with the same reaction, if we are going to remove H2 or I2, so we're going to remove some reactants from that reactant bucket now. And so what would have to happen is water would have to flow from our products bucket to restore what we had lost. So we're going to shift towards the left or towards the reactants in this case. All right, now what about if we were to remove product? So if we remove product, we're going to have to replace that product that's been removed. And so in this case, we'd have to flow towards the right or towards the product side in order to replace that product that's been removed. And this is a trick that's used by chemists quite frequently. So if you can somehow remove one of your products by like boiling it away as a gas or condensing it as a liquid and pulling it away, if you can somehow remove one of your products, the reaction is going to keep going the forward direction and make more products. So more on that later. You'll see that some talk about that at the end of this video. So moving on, let's talk about how pressure affects things. So if we change our pressure, that's going to shift our reaction. In order for our reaction to shift, though, we have to have gases involved, and we have to have different number of moles of gas on each side. So again, if we have no gas, or if we have equal moles of gas on either side of the equation, pressure will have no effect. Now if we decrease the volume, and by decreasing the volume we're going to increase our pressure, what's going to happen is we've given our reaction less space. And so gas is the state of matter that takes up the most space, so we will have to get smaller to fit in this smaller space. We're going to shift towards the side with fewer moles of gas. So in the example that's given right here, we have on our left side here, we have 1, 2, 3, 4 moles of gas on the left side, and on the right side we have just 2 moles of gas. So again, we have 1 N2 and 3 H2, so that's 4 moles of gas on the left. 2 NH3s is just 2 moles of gas on the right. Now, if we do the opposite, if we increase the volume, which decreases the pressure, we've now given our reaction more space. It's going to shift towards the side with the larger number of moles of gas. So in this case, it would shift towards the reactants. And the reason for this is, again, gas is the state of matter that takes up the most space. If we give our thing more space, it's going to shift towards that side that takes up more space. In this case, it happens to be the reactant side, but it'll vary from reaction to reaction. In some cases, the product side has more gas. You'll see both types. All right, so that brings us to our last one, which is how temperature affects endothermic reactions. So with an endothermic reaction, these are reactions that absorb heat. And so in an endothermic reaction, heat's actually considered a reactant. So we can write our equation right here with heat on the left side because it's a reactant. We can almost think about this as like a chemical. So if we increase our temperature, what that means is that we have added heat, we've added more reactant. So to use up the excess reactant, we're going to shift towards the product side. In other words, we're going to consume the extra heat and make more products to restore balance. Now, decreasing temperature has the opposite effect. So if we decrease our temperature, we're going to remove our reactant. We'll have to shift towards the reactants or towards the left side in order to reestablish balance. So again, adding heat for an endothermic reaction will shift us towards the right or towards the products. Removing heat will shift us to the left or towards the reactants. All right, so right here, let's talk about when we have an exothermic reaction. So for an exothermic reaction, reactions that release heat, heat is going to be a product. And so we're going to see the opposite effect here. So if we increase our temperature, now that's actually going to shift us towards the left or towards the reactant. So we're going to have to use up the extra heat we've added to increase the temperature. We're going to have to shift to the left towards the product or towards the reactants to do that. And if we decrease our temperature, then that's like removing a product, and we're going to have to shift towards the products or towards the right to replace that product that we're removing. All right, now let's summarize LeChateliers principle. We see that concentration is going to be able to cause our reaction to shift. And so what we see is that if we add a chemical, we're going to sort of shift to use up the excess chemical we've added. And if we remove a chemical, we're going to shift to replace it. Volume's important because this is going to affect the pressure. So if we have differing moles of gas on each side, increasing pressure will shift us to the side with fewer moles of gas. Decreasing pressure will cause us to shift to the sides with more moles of gas. And with temperature, what we see is that our heat can actually be like a product or reactant. So for endothermic reactions, we treat heat like a reactant. We think about concentration of that heat. And for exothermic, we treat it like a product. Then finally, if we add a catalyst, there's actually no effect. Although it speeds up our reaction rate, it speeds it up equally in each direction, so we won't see a shift in our equilibrium in this case. So I'd like you to now pause the video and please complete questions 1 through 4. All right, welcome back. Let's take a look at an example. So here's our applied example, and then once we finish talking about this, you're going to want to complete the applied example in the worksheet. So this is how ammonia is made. So this is a super important chemical reaction. This one really kind of changed the world in terms of both agriculture and, unfortunately, warfare as well. So we take nitrogen, we react it with hydrogen to form ammonia, and this reaction is exothermic. It also releases heat. So if this reaction is exothermic, we'd want to run this reaction under a relatively low temperature, because that's going to give us the greatest amount of product forming. So again, for an exothermic reaction, the lower the temperature, the more the product is formed. Unfortunately, we have a problem. In the real world, it's more complicated than that, because in the real world, the lower the temperature, the slower our reaction. So we have to find that balance between a temperature that's low enough we get a good amount of ammonia, because our goal here is actually to make ammonia. That's the stuff we want from this reaction. So a lower temperature is going to favor more ammonia formation, But unfortunately, that lower temperature is also going to make the reaction slower. So we have to also run the reaction at a high enough temperature that our reaction rate is going to be fast enough. So in the real world, it's really hard to get all this stuff to work out. Additionally, if we look at this reaction, we have 4 moles of gas on the left side, and on the right side we have 2 moles of gas. And so what that means is that we're going to want to run this reaction under high pressure. And because theoretically, the higher the pressure, the better the yield of ammonia is going to be. Unfortunately, once again, the real world is kind of complicated because ammonia is poisonous and hydrogen is very flammable, and if the pressure in our machine is too high, it can spring a leak or it can break a pipe, and then we're in a really bad situation because we're spraying a bunch of flammable hydrogen around and a bunch of poisonous ammonia around our factory. So we want to use the highest pressure where our machinery is still going to be safe and we're not going to have much risk of explosion. And then, so the way that people do this is they pump in hydrogen and nitrogen into a compressor, because we want relatively high pressure, into a catalyst chamber, because it's going to speed our reaction up. Then we end up with a mixture of these 3 gases. And then scientists do a really clever trick right here. So what we see is that nitrogen is nonpolar, and because it's nonpolar, we have just dispersion forces. So we require a really low temperature to liquefy it. So as you're probably aware, if you've seen Terminator 2, liquid nitrogen is very cold. And so therefore, we have to get it really cold to get the nitrogen to liquefy. Hydrogen actually is nonpolar as well. We have dispersion forces. So again, we have to get this thing really, really cold in order for it to liquefy. But ammonia, on the other hand, is very polar. Ammonia forms H bonds. And so it's a strong intermolecular force. That means that ammonia liquefies relatively easily. So although it's a gas at room temperature, on a cold winter day, this stuff would actually be able to liquefy due to those strong H bonds. So we're going to pump our mixture of gases into this condenser, which is basically just a really cold chamber. And the ammonia, because of the hydrogen bonds, is going to liquefy. We can drain it away. And we can take our leftover unreacted N2 and H2 and just pipe them back into the system. So we can keep just circulating this around over and over, making more and more ammonia, and we keep removing the ammonia as a liquid to drive the reaction forward. So very clever stuff, and in the real world this stuff's quite complicated because you can't always use the exact temperature and exact pressure that LeChateliers Principle sort of dictates is best. You have to sort of take into account real world considerations. So congratulations, you survived this video. Have a great day.